I have an idea. It's a very simple idea. That idea being the fractal geometry of entrapped space-time manifolds within one another, each a universe to itself. By exploring this idea, we will answer the most pressing questions in physics. Why is the universe flat? What happened to the antimatter at the time of the Big Bang? What caused the dipole and the large-scale anisotropies of the cosmic microwave background radiation to be formed? To begin, what is a manifold? Space and time are one. Together, they are space-time, acting as a single structure within Einstein's theory of general relativity. This structure as a whole we call a manifold. The number one example of a manifold is our universe as a whole. It is the fabric of space-time that sets the stage upon which the evolution of our universe unfolds. In order to measure distances and angles upon a manifold, we employ a Lorentzian metric. This metric in turn describes how we go about measuring said distances and angles. Together they set the stage by which the orbits and paths of astrophysical objects in relative motion with respect to each other can be predicted. That predictive power comes from Einstein's field equations of general relativity. General relativity describes how the space-time fabric of a manifold is curved and warped by the presence of mass energy density. For example, our Sun, composed primarily of hydrogen and helium, has a mass of about 2 × 10 to the power of 30 kilograms, with a spherical diameter of around 1.4 million kilometers. This concentration of mass within the Sun curves and bends the fabric of space-time. By how much and to what extent is found by using a solution of Einstein's field equations. We know that the Sun warps the fabric of space-time in observing how the path of light changes as it passes by our Sun. Photons emitted by a distant star travel across the interstellar expanse of the universe's space-time manifold. For the greater part, they mostly follow a straight path, as the curvature of an empty vacuum is flat, as described by Einstein's theory of special relativity. But if their path comes close to a large object, such as another star, then the path is curved around the star, the mass of the star causing this manifold to be curved. It was this observation by Sir Arthur Eddington in 1919, using a solar eclipse, which showed that the path of light from known stars, when seen next to the Sun, was visibly altered by the mass of our Sun. It was this experiment that confirmed Einstein's theory of general relativity. In essence, we can think of a manifold, such as our universe, as being like a sheet that is curved by the presence of physical objects composed of mass. Even if that mass is invisible, itself entrapped, such as is the case with dark matter. Although completely invisible, we see the effects of dark matter where it acts as an intergalactic lens, curving the path that light travels along, producing these beautiful Einstein rings. The light emitted from galaxies behind the dark matter lens travels along curved paths whose curvature is formed by the presence of dark matter. Collectively, The dark matter acts as a lens, magnifying the galaxies behind the lens. As for what exactly dark matter is, well, in order to understand that, we need to talk about entrapment and our idea of entrapped manifolds. The definition of what an entrapped manifold is given form in considering the extreme logical endpoint of general relativity by way of a black hole. There are several types of black holes, depending upon the solution to Einstein's field equations. The simplest and most commonly known type is called the Schwarzschild black hole, named after Karl Schwarzschild, who found the first exact solutions to Einstein's field equations in 1916, which describes the gravitational field outside a spherical body with no angular momentum. The idea of a black hole was given form in considering a spherical body with infinite mass in an infinitely small point, the gravitational singularity. Here, the gravitational field is so strong that not even light could escape its pull. A non-rotating black hole has only one physical object inside it, and that is the gravitational singularity, a point of infinite density. The spherical event horizon that envelops this singularity is defined by the escape velocity being equal to the speed of light. Above the event horizon, a photon of light may escape back out into the universe, but below the event horizon, the photon becomes entrapped, caught in the gravitational field of the singularity, unable to ever escape. As nothing can travel faster than the speed of light, it becomes impossible for anything trapped inside the event horizon to ever escape it, including light. In total effect, the black hole contained inside the volume of the event horizon can be considered its own entrapped manifold, wherein every path traveled leads down and onto the singularity. There is no other path of travel out or away from the singularity once we are inside the event horizon. Once inside the volume of the event horizon, there is no escape, and we are entrapped. Physicists visualize this entrapped manifold by way of a Penrose space-time diagram showing a Schwarzschild black hole. Here, the infinite manifold that is our universe is conformally mapped into the finite diamond with the vertical blue lines representing time and the horizontal red lines representing space. Next to it, the black hole is drawn as a separate manifold which maps to the interior of the black hole. The 45-degree boundary between the universe manifold and the black hole manifold is the event horizon of the black hole. Inside the black hole manifold, all paths lead down to the inevitable gravitational singularity. The important part in considering this Penrose diagram of a Schwarzschild black hole lies in the separation of our manifold, the universe, from the entrapped manifold that is the interior of the black hole itself, the event horizon being the boundary between the two manifolds. The fate of anyone falling into such a black hole is to fall onto the singularity. The fact that black holes exist inside our universe shows that entrapped manifolds exist inside our universe and are a very real thing. This very simple description of a black hole does not account for rotation, as Karl Schwarzschild's solution of relativity assumes the angular momentum of the body is zero. It took until 1963, a near 50 more years, to find a solution to Einstein's field equations where rotation of the astrophysical body is non-zero. Named after its discoverer, Roy Kerr, the Kerr metric can be used to describe a rotating black hole, as opposed to one with no rotation. With rotation, the resultant Penrose diagram of a rotating Kerr black hole transforms into something else, a doorway to another universe. What happens is that with rotation, the point singularity of infinite density is spun out into being a ring of infinite density, a ringularity. The formation of this ringularity fundamentally changes the structure of the black hole as a wormhole opens up inside the ringularity. This changes the fate of someone falling into the black hole from an inevitable end of falling onto a singularity to one where we fall through a wormhole. Viewing the full Penrose diagram of a Kerr black hole, we see that it is separated into a series of manifolds. An object falling past the event horizon of a rotating black hole will fall down and through the wormhole. Traveling through the wormhole, we arrive at another entrapped manifold, the white hole, whose direction of travel is away from the wormhole and out into either one of two parallel new universes. The common depiction, popularized in science fiction, of a wormhole is as being like a bridge across space-time, or in this case, the wormhole at the center of the rotational black hole leads to a pair of separate universes whose spatial location are completely removed from our own universe. That is, we think of one universe as being its own bubble manifold of space-time, and the other new pair of universes existing as their own separate manifold bubbles of their own reality. It is at this point we are looking to propose a different interpretation and introduce a wholly new but revolutionary idea. So everything up till now is established physics. It is here we consider just the subtlest of ideas. That idea being that rather than those two new universes being separate manifolds in their own right, they actually coexist inside our universe, showing the same volume of space as our universe. In effect, these two new universes are located inside our universe. How? Well, rather than this wormhole being a bridge across space-time, it is in fact going nowhere. It is not a bridge across space-time projected through, say, a hypothetical higher dimensional bulk, but rather this wormhole inside the rotational black hole leads nowhere, meaning the entrance and exit to the wormhole exists inside the absolute volume of the black hole. The rotational black hole is an entrapped manifold, which in turn entraps the wormhole's manifold. So what makes us assume the wormhole is a bridge to another dimension or reality? Rather, we consider the idea that the exit of the wormhole is located within the volume of the rotational black hole, meaning the associated white hole leading from the wormhole exists within the volume of the rotational black hole. The two new universes, each the parallel of the other, are themselves entrapped manifolds whose actual spatial location is inflating forth from the polar regions of the rotational black hole. The surrounding parent universe coexist spatially together but are in fact temporally disconnected from one another. Like a pair of balloons, the inflation and growth of these two child universes are into the polar regions of space surrounding the black hole. The inflation of these two child universes is driven by the flow of space-time in from our parent universe into the rotational black hole, through the wormhole, and out via the adjoining white hole, meaning the parent universe coexists spatially but not temporally with the pair of child universes. So, if we ask the question, what is the child universe expanding into? Then the answer to that question is the spatial volume adjacent to the polar regions of the associated black hole that gave birth to it. Now, if we ask the more specific question, what is our universe expanding into? Well, let us consider the answer given by mainstream cosmology. The answer is nothing. Or to quote X's Grok, the universe is expanding, but it's not expanding into anything in the way we might imagine, like a balloon inflating it into a larger room. This is completely counter to the idea we are considering. Here, we are actually imagining a child universe as being like a balloon being inflated inside a larger room, the parent universe. By considering this, as we're about to see, such an explanation allows us to answer the most basic questions in cosmology in quick and rapid succession. Given that the overall shape of the child universe is determined by the local space-time curvature of the parent universe, then the shape of the child universe is determined by the space-time curvature in the region surrounding the black hole back out in the parent universe. Meaning, if the space-time fabric of the parent universe, in which the child universe as a whole, becomes warped, then the shape of the child universe is warped by its parent's curvature. Using our analogy of a balloon being inflated inside a room, let us imagine a gravitational wave passing through said balloon. With a gravitational wave, the fabric of space-time contracts, expands, contracts, and expands. A meter length contracts and then again expands as a single gravitational wave passes through it. So too does the shape of the balloon contract and expand as the gravitational wave passes through it. The child universe, being like a balloon as a whole, will contract and expand as a gravitational wave of the parent universe passes through it. Now, the vast majority of space is vacuum with nothing in it. So, it is a reasonable assumption that the child universe is expanding into the vacuum of the surrounding parent universe. Special relativity specifically tells us that the local curvature of a vacuum is that it is flat, meaning the surrounding parent universe into which the child universes are expanding are themselves also flat. Thus, the overall shape of the child universe as a whole is going to be flat. For the greater part of the 20th century, the question, what shape is our universe, has been of prime importance to cosmology. The question of shape arises from considering parallel lines. On a flat surface, parallel lines never cross or diverge. The distance between the lines is always the same. Alternatively, on a surface with positive curvature, such as a sphere, parallel lines converge and cross over each other. Then, on a surface with negative curvature, such as a saddle, parallel lines diverge away from one another. In asking the question, what shape is our universe, cosmologists were looking to answer the question whether parallel lines would remain parallel or not. After much debate and observations, the question to what shape is our universe was given answer, the answer being that the universe is flat. From examination of the cosmic microwave background radiation to surveys measuring the total energy density of the universe, through to cosmic surveys of large-scale structures, the evidence clearly shows a universe whose overall shape is one that is flat. So, in considering the idea of a child universe expanding into the vacuum space of its parent universe, we immediately have an answer as to why we live in a universe that is flat. Our universe is flat because it is expanding into the vacuum space of the parent universe that gave birth to us. How simple is that? The alternative explanation, in asking Grok again, is that the universe is flat because cosmic inflation smoothed out any curvature in its infancy, stretching space to appear Euclidean on large scales. Its expansion into nothing simply means space itself is growing, not that it's filling some external void. Meaning, the standing explanation as to why our universe is flat is because of cosmic inflation, given that our universe is not actually expanding into anything. Cosmic inflation itself is driven by a hypothetical scalar field for which no experimental evidence has been found. For example, no particle representation of the inflation field has ever been seen. So given that our universe is expanding into nothing, there is also the mainstream idea that our universe came from nothing. I mean, the first law of thermodynamics, the conservation of energy, states energy can neither be created or destroyed. But yet, our mainstream explanation for the Big Bang says our universe came from nothing and is expanding into nothing while inventing hypothetical quantum fields in order to explain the observational evidence that our universe is flat.
Really?
Occam's razor says the simpler explanation tends to be the one that is true. On the one hand, we can imagine our universe, like a balloon being inflated, is expanding into the vacuum space of our surrounding parent universe, which I herein call the superverse. This is a whole lot more intuitive than trying to imagine what nothingness actually is. As a note, our universe occupies a subset of the volume of the superverse. So using set theory nomenclature, I call it the superverse, as it is the superset to our own universe. This superverse has its own law of general relativity. Same mathematics, but operating at a much larger scale. A Planck length in the superverse could be a meter, it could be a parsec. The point being that it operates at its given scale, and its given scale compared to ours is truly titanic. The key philosophy of fractal geometry is that self-similar patterns repeat, irrespective of scale, and this gives us mathematical permission to imagine such a superverse. Exactly like our own, a fractal mirror, but for one of scale. Then, just like our universe, the concentration of mass energy density causes the curvature of the supervertices space-time fabric to be curved and warped. Our universe's shape as a whole is warped and shaped by the curvature of the superverse within the volume it has expanded into. Close to the black hole, the curvature will be great, but the further the universe expands away from it and out into the vacuum of the superverse, the curvature flattens out, as the curvature of the vacuum in the surrounding superverse is itself flat, implies that the shape of our universe as a whole is flat. In comparison, the alternative mainstream explanation sees ourselves making up hypothetical fields while violating the first and most basic law of thermodynamics by creating the entire universe from nothing. Honestly, these days, I don't know whether to laugh or cry about the state of modern theoretical cosmology. For example, cosmic inflation says that tiny quantum fluctuations in the very early universe expanded to very large scales during its period of very rapid inflation, the evidence of which, it claims, is to be found in the cosmic microwave background radiation. But when it actually comes to the observed and measured cosmic microwave background, the actual main results are ignored and argued away as not being part of the microwave sky. What am I talking about? The CMB dipole and the large-scale anisotropies seen in both WMAP and Planck, to name but a few. Starting with the CMB dipole, which has the greatest temperature gradient of all the features identified in the microwave sky. Ever since its discovery in the late 80s, the CMB dipole has been explained away as a Doppler shift that arises because of Earth's movement through the universe relative to the rest frame of the microwave sky. But numerous studies of quasar groups have shown that this kinematic interpretation of the CMB dipole is actually invalid. So what caused the CMB dipole? Returning back to picturing our universe as expanding forth from a black hole and expanding out into the expanse of a much larger parent universe, the superverse, I noted that there are two expanding child universes. One expands from the North Pole, and the other expands from the South Pole. We consider two universes because, firstly, in the conformal solution of the curve metric, the white hole exits into one of two universes. Secondly, following CPT symmetry a fundamental law of quantum mechanics, a universe of antimatter would be a manifold traveling in the polar opposite direction to our own. In this way, we are able to not only account for what happened to the antimatter at the time of the Big Bang question, but also in doing so, we see why our parallel universe of antimatter is exactly that. It is a universe of antimatter because the expansion of that universe is in the exact polar opposite direction to the expansion of our own universe. Specifically, there are two poles to a rotational body such as our black hole, one north pole and one south pole. The expansion of each universe is from each of the two poles. One universe expands into the region above the North Pole, and the other universe expands into the region below the South Pole. Given this interpretation, we can see that the expansion of each universe is unidirectional. Given this unidirectional expansion of our universe, we would expect to see one half of the microwave sky to be very much significantly hotter than the other. Or rather, in asking the question, what caused the CMB dipole, then our answer is that it arises from the unidirectional arrow of travel away from the black hole's polar region. That's 3 questions answered. Why is our universe flat? What caused the CMB dipole? And what happened to all the antimatter at the time of the Big Bang? Okay, let's keep going. Now, about those large-scale anisotropies seen in both WMAP and Planck. Here we can see in the southern hemisphere 2 large spiral arms, one hot and one cold. I would love to present you with an alternative explanation for mainstream cosmology, but in truth, this reproduced result is barely even given the time of day by theorists. Why? Because theoretical cosmologists have no explanation except to dismiss it. Unfortunately for them, a new study using Planck's CMB data has confirmed that the universe is significantly more clumpier in the areas of these large-scale anisotropies, meaning they are physically real structures within our not-so-perfectly homogeneous universe. In developing my Big Bang Kilonova Hypothesis, I propose that these twin spiral anisotropies are caused by the gravitational waves within the parent superverse. These gravitational waves of the superverse are generated by the inward death spiral of 2 neutron stars in said parent universe. Just like in our universe, a pair of neutron stars spiraling in towards each other generates spiraling gravitational waves. The superverse, operating by its own form of general relativity, generates twin spiral gravitational waves. We say this because the mathematical law of fractal geometry is that self-similar patterns repeat, irrespective of scale, even if the size of that scale is larger than the entire universe as a whole. After all, instead of trying to make stuff up about how the Big Bang singularity was born from nothing, we study how a singularity is actually born inside our universe in order to build a Big Bang theory that can explain the observed microwave sky. Having previously stated that the overall shape of our universe is determined by the local space-time curvature in the parent superverse, then the presence of these twin spiral gravitational waves would warp our very early universe, leaving their imprint. Of course, it is very important to note that immediately following the collision and birth of a new black hole, the generation of gravitational waves ceases and the surrounding region flattens back out. Following the space-time curvature of our parent superverse, one spiral wave creates a spiral trough into our very early universe. This trough fills up with the primordial plasma of the early universe. Vice versa. The other spiral wave creates an indentation into our universe, pushing aside the primordial plasma. As the gravitational waves recedes, the shape of our early universe then flattens out, but the spiral waves have left their mark. The spiral wave that created the trough filled with primordial plasma would then go on to become the hot spiral arm. The surrounding regions, in turn, being filled with more plasma, would have a far greater than average density with respect to the rest of the universe. This feature we see in the newly identified and named hemispherical power asymmetry in the CMB. Vice versa, the cold spiral arm comes about because the plasma has been pushed aside, implying that when the wave recedes and the universe flattens back out, what remains is empty void. From this, we are able to make the prediction that one side of our universe should contain much more mass with respect to the other side. Namely, I would expect the area where the hot arm is located to be filled with the additional matter that accumulated in the trough created by one of the kilonova's gravitational waves. Of course, as the wave recedes, the trough flattens out, flinging this matter into the surrounding regions. Coupled to this, I would predict that region where the cold spiral arm is located would contain much less matter, a spiral void having been created when the other gravitational wave in the kilonova receded. And this is exactly what a new study has found, backing up confirmation that these spiral arm anisotropies are in fact part of the cosmic microwave background radiation. So, with one explanation, that being our universe is shaped by the local space-time curvature of our parent superverse, we have been able to explain the large-scale anisotropies and the fact that we see the shape of our universe as being flat. Then, in considering the expansion of two universes, we are also able to give answer to the mystery of antimatter at the time of the Big Bang, as well as explain the CMB Dipole. All this from the simple consideration of one idea. That idea being that our universe is an entrapped manifold that was born from and is expanding inside a pre-existent parent universe. In doing so, we have given simple answer to some of the most fundamental and pressing questions in all of modern physics. And some of those questions have not been answered by anyone else in the field of physics apart from us herein. And this is only the beginning. Until next time.